welcome back. In this lecture, we are going to look at ideal gas mixtures, and subsequently we will be looking at partial molar properties, particularly how it is evaluated or calculated from experimental data. So, for an ideal gas, we are all aware of the equation of state, right? P v is equal to nRT, but for ideal gas mixture, we can extend that and write as P v is equal to summation of Ni, number of moles, multiplied by RT, okay, where I is equal to 1 to m. So, this we can sometimes also call volumetric equation of state, okay, because the volume is related with temperature and pressure. In addition, since ideal gas is a non-interacting system, okay, which means basically they are not interacting at all, you can sum up the internal energy of individual component. Okay. Now, we know for ideal gas internal energy is only a function of temperature. So, essentially this is a function of temperature. We can also write this as summation of number of moles of each component multiplied by molar internal energy of the component I, which is also function of temperature. Okay. So, this is sometimes also called thermal equation of state. Okay. Now, what I am interested basically is obtaining the partial molar volume for ideal gas. So, we can use this expression, okay, and get V is equal to summation Ni divided by P RT, okay. And now we can obtain Vi, which is a partial molar property of component I for the ideal gas, as simply del V by del Ni, keeping temperature, pressure and all other component mass or the moles constant. Okay, so, if you do this exercise, I can write this V as summation Ni or Nt, the total number of moles multiplied by RT and this is going to be simply RT by P. Okay. Now, which is nothing but actually the molar volume of a component I occupying the same volume basically. Okay. So, this is nothing but the Vi, which is a pure component molar volume, which occupies the same volume having a moles Ni. Okay. So, this is something which we have also done in our earlier thermodynamics courses. Okay. So, I can summarize that for ideal gas mixture, Vi is nothing but Vi and Ui, the partial is nothing but Ui. Okay. Now, in general for ideal gas mixture, I can generalize this what we have calculated now as for any extensive thermodynamic property, the partial molar property of that for an ideal gas at a given temperature and pressure is equivalent to its molar property of the pure system for a component I at that temperature, but its own partial pressure. Okay. So, this is a molar property. Okay. So, you understand this aspect that when you contain this I components in a volume V, okay, the number of moles I for species I is basically occupying the same volume, but with a pressure Pi basically. Okay. Now, this we are going to use it later when we are going to derive little bit more. So, this is a generic property for an ideal gas, not for all, only for ideal gas mixtures. Okay. Now, I am just going to quickly do this exercise. Since for ideal gas U is equal to function of temperature, that means basically the partial derivative of U with respect to T, which is nothing but Cv. Okay. This is only a function of temperature, that means I can write as this, and this is nothing but Cv, which is also a function of temperature. This implies that for an ideal gas. Okay. Similarly, H is equal to U plus PV, which is because PV is nothing but NT RT, which is also a function of temperature. So, del H by del T at P for all n, it can be written also in a similar form, which means this is okay. So, this is something which we know, and we are going to make use of it whenever we are going to apply ideal gas approximation for mixtures. We can also use these approximations to get the changes in the internal energy with respect to temperature by making use of heat capacities. Okay. Now, what I am trying to obtain expression for internal for entropy and Gibbs free energies and Helmholtz free energies for an ideal gas mixtures. Okay. So, let me just start with the first law. Okay. Now, from here we are going to extract ideal gas. So, I can rearrange S in this form, ds is equal to 1 by T du plus P by T dV. Okay. Now, if you consider that the system is at constant temperature, then what I get, this is, because it is constant temperature, all other things are changing, that means the internal energy is a constant. Why? Because U is a function of temperature for an ideal gas mixtures. So, ds is nothing but P by T dV. Okay. Now, for an ideal gas mixtures, I can write this because I know volume is summation Ni by P RT. So, I can now get a derivative of this. So, this summation Nt I can write as N, summation Ni I can write as Nt. So, this becomes Nt total number of moles RT d of 1 by P, or I can rewrite as, because T can cancel, now I can rewrite as minus R N T d log P, okay, in a simpler form. Okay. So, the ds is okay. Now, if I divide by total number of moles, then I can also write this expression as d small s, which means molar property, minus R d ln P. I can also write in this form, both are equivalent. Okay. Now, what is my interest is to obtain ideal gas, entropy of the ideal gas. So, this is the expression for an ideal gas expression in the differential form at constant temperature. So, we are going to now integrate from Pi, okay, the partial pressure of component I in the mixture, to P. Okay. So, that we are going to integrate. Now, let us see what we get. So, considering the molar expression, so I am going to get S small s I, okay, ideal gas, I am going to put that temperature T P minus okay, that is going to be equal to minus R ln P by Pi, okay, because that is simple expression which we are, there is nothing else. Okay. Right. So, now, so basically this expression holds for ideal gas mixture, and this is a molar property. Okay. So, when we integrated, we got this expression. Now, what is Pi? Pi is y times P. So, I can get an expression now, this as minus R ln P YIP, and this is equivalent to R ln YI. Okay. So, I have an expression now. I have an expression. Okay. So, this is the expression here, of course this is T comma Pi. Okay. Remember that. Okay. So, this is for an ideal gas, okay, at Tp. Now, if you recall, this is what we made a statement here that for an ideal gas this expression holds. For all properties, extrinsic property, we can write in this way. So, what we calculated here is basically the left hand side. For if you replace m by s, then mi Tpi is nothing but Si Tpi, and this can be now replaced by the partial molar property of S. So, this is nothing but equivalent to saying that this is equal to Si bar T and P. Okay. So, this is an expression for us now. Now, this is in terms of the molar property. I can also write that total S for ideal gas, or in general can be written as Ni Si bar, okay, at the same temperature and pressure. So, this is, we know this is true for in general properties, and now I can write for an ideal gas Ni Si Tpi. So, that means this is equivalent to saying that for an ideal gas summation Ni Si Tp minus R summation Ni ln Y. So, this is basically for an ideal gas mixture. Okay. Okay. Now, using this expression we can derive other properties, that would be your G and H. So, let us look at first G. G is by definition is H minus Ts, and for a partial molar we can write this as. Okay. Now, what would be the, for ideal gas, what would be Hi bar? So, let us look at H. H is U plus PV. Okay. U, of course, we can write as Ni Ui, okay, because of the fact that it is an ideal gas non-interacting system, and PV is summation Ni RT H. Now, which essentially means this is nothing but summation Ni Hi, which essentially you can mean that if you take a partial derivative of H keeping the other moles constant, then Hi bar will be equal to Hi. So, this is for ideal gas system. Okay, you can replace Hi bar in the G expression by small hi. Now, this Si bar, the partial molar property of entropy, can be replaced by this expression. Okay. So, this is what we are going to do in order to get Gi bar. So, let me just plug in these values. So, Gi bar, okay, is Hi minus T Si bar, and now I am going to replace T Si bar by this expression, okay, because Si bar is there. So, I am just going to take the one which is the expression which we have derived here, okay, which is small si Tp minus R ln Yi. Okay. So, this is the expression. So, this is can be written as minus, because Hi is also at Tp, Si is also at Tp. So, this is written simply like this, plus RT ln Yi. Okay. Now, this is nothing but small gi, okay, plus RT ln y Gi bar. Okay. Now, what is Gi bar? Gi bar we have already defined it earlier. Gi, that partial molar gas free energy for a component I is equal to chemical potential of that component I, right. So, this is nothing but mu I. Okay. So, now I can make use of the fact that G is nothing but summation Ni Gi bar. So, I can get the G as summation Ni Gi plus R summation RT summation Ni ln Yi. So, this is the expression for my G. Okay. Now, similarly, I can actually extend this exercise for Helmholtz free energy, and this is going to be now in a similar way Ai plus RT summation Ni ln Y. Okay. Remember that this is at temperature Tp. Okay. Okay. So, similarly, this would be also at temperature Tp. Okay. Now, for an ideal gas, we know that Cp minus Cv is equal to R for the ideal gas mixture. You can also derive that. So, Cp minus Cv can be shown to have this following expression: T del P by del T at constant volume, keeping all the moles constant, del V by del T, P and constant. So, if you plug in the equation of state for ideal gas, you can show that this is nothing but Ni R. Okay. So, this is something which you can derive. Now, you may be asked like how does the ideal gas properties G, A, H behaves as a function of composition for ideal gas. Okay. So, I can just draw a schematic form that how it looks like when you plot such a function for ideal gas mixture. So, it is going to be a little bit messy, but let us see if we can draw it well. So, this is y from 0 to 1. Okay. For 1 the property would be let us say 1, and for 0 it would be let us say 2. So, I am going to draw first entropy. So, it may look like this. Okay. So, this is like a molar property of 2, PO2 component is a molar property of component 1. Okay. This may look like for enthalpy. Okay. This may look like for internal energy. Okay, and this may look like for volume, molar volume. Okay, and this may look like for the Gibbs free energy. Okay, G1, G2. Okay, so somewhere it's showing minima also for G. Okay, so this is a schematic form that how does this behave as a function of Y for simple ideal gas mixture. Okay, for binary component. Okay, so with this we will stop here. Okay, we will continue this exercise in the next lecture.